Hi class. Okay, so for today we will learn and talk about the new chapter is the galaxies and the dark matter. So we will learn this five content. Okay, in this chapter we have about the dark matter, the galaxy collision, galaxy formation and evolution, black hole, and also the universe of a large scale. Okay, so maybe we can recap. For the previous, we have learned about the dark matter halo, okay, the surrounding of our galaxy, and to study the effect of dark matter now on the large scale, and we need a way to calculate the masses of galaxy and the galaxy cluster. So this is the figure here is the black eye galaxy set up of M64. Okay, so the masses of some spiral galaxy can be estimated by determining their rotation curve and using the Newton's law. So the figure is about the rotation curve, imply the masses of this and lie within the 25 kiloparsec of the center of nearby spiral galaxy here. And we can see also in this graph is a rotational speed curve graph with the distance from the galactic center. Okay, if you can see, for most of this distance from zero distance, okay, here until on a certain stage, okay, so the rotational speed will begin to be constant or consistent, okay, here along the distance when the distance from galactic center become more wide. All right. So, however, the distance galaxy are too far for such detailed curve to be drawn, and instead we can measure their mass via the spectral line broadening and Tully-Fisher relation to measure their overall rotation speed. And similar technique, okay, which have been applied to the elliptical and irregulars and useful for measuring mass lying within 50 km per second of a galaxy center. Okay, so to probe further from center of galaxy, we can turn to orbiting the binary galaxy system. Okay, so here is the figure of the observer which seen the spiral galaxy here, and we have the red shift and also the blue shift coming. So the orbital periods of binary galaxy system are typically billion of years, and this result in the orbit semi-major axis and periods. So we have the we can obtain the quite reliable statistical information about galaxy mass, and the galaxy mass range about normal, spiral, and large is here, irregular galaxy, and the dwarf, elliptical, and dwarf, irregular range. Okay, so to measure the mass of the galaxy cluster, we can also observe the motion of many galaxies in it, then estimate how much mass is needed to keep the cluster gravitational bound. And here is the expression to find the galaxies in a gravitational bound cluster. Okay, so this is the expression, and rearrange this to get this m here, rv squared over g. So now the cluster mass obtained about this range. Okay, so the rotation curve of the spiral galaxy will remain almost flat far beyond the galaxy visible image, and contain large amount of dark matter in the form of the visible dark holes. Okay, so overall, the spiral galaxies seem to contain 3 to 10 times more mass can be accounted in the form of luminous matter. And the studies of the elliptical galaxies suggest similarly large dark holes around them, and it contains 10 to 100 times more mass than the content by luminous matter. So this leads us to believe that 90% of the matter in the universe is dark, okay, and their mass undetected at all wavelength. So the accumulation of the dark matter within each individual galaxy and their dark holes are not enough to account for the total dark matter. And we have the intra-cluster gas is a super hot diffuse intergalactic matter filling the space among the galaxy and detected the substantial amount of X-ray radiation. Okay, for example, here we have this Abell 1835 with hot gas filling the intra-cluster space, okay, in the blue cloud here. Good. So if we zoom in this part, then we can see very detail of the blue, the content of the blue cloud. Okay, and also it has found in the radio lobes of head-tail radio galaxy. For example, here we have this NGC 1265 that appears to be swept back by some onrushing wind, okay, travel through this medium of Perseus cluster. Okay, this is the observation that reveals at least as much matter that exists within the cluster in the form of hot gas, and it still doesn't solve the dark matter problem. Okay, so the intracluster gas is thought to be mainly primordial, and it also contains some heavier elements such as carbon and nitrogen. So the galaxy collisions, okay, with the thousand of member galaxy orbiting within a few megaparsecond in the galaxy center, and collision among the galaxies are common. So we have this Cartwell galaxy, and the ripple, that means the halo of young stars, okay, that shows is most likely a density wave created by the passage of the smaller galaxy through the disk of the large one. Okay, so we have both spiral galaxy here are apparently passing each other in a counterclockwise direction, and bursts of a star formation and the dust within a push, shove, and shock. Okay, the gravitational forces during the interaction between two galaxies will compress the interstellar gas and result a galaxy-wide episode of the star formation. Okay, so the result is a starburst galaxy, for example, this two with a bluish tint. Okay, and now is the computer simulation. Okay, so this computer simulation are used to model in detail the gravitational interaction among stars and gas also within the galaxy. And the effect of a collision between the galaxy could be understood, and the eventual outcome of the interaction could be estimated. So this figure is a simulation of the two colliding spiral galaxy. Okay, and this is the antenna galaxy, show the extended tails and double galactic center. Okay, star formation that induced by the collision is clearly traced by the blue light from thousands of young hot stars. and this simulation indicate ultimately the two galaxies will merge into one. Okay, so the extensive dark matter halos will surrounded with the galaxy, making them much larger than their optical appearance, and it suggests making the interaction and mergers of at all more likely when two galaxies approach one another. The interaction between their dark halos slow the galaxy's motion, and that halo matter is then redistributed between or ejected from the system and will result in a change in their original orbit. Okay, so if you have small group of the galaxy, so the galaxy speed are low enough, okay, and tend to merge together, but in large groups, okay, so the galaxy will move faster, tend to pass through the one another. Okay, and the Andromeda Galaxy is currently approaching the Milky Way at 120 km per second, and both will collide in a few billion years. Although the collision may wreck the large-scale structure of galaxy, it has essentially no effect on the individual stars. Okay, so when the two galaxies collide, their star population will get double, but their content will get rearranged. Okay, so spectacular bursts will be produced, but the individual star will just glide and pass one another. So, astronomy note the simple no simple evolutionary connection among the various of the categories in the Hubble sequence. So the theory of galaxy formation and evolution is still very much its infancy, since galaxies are more complex than stars. Galaxies are harder to observe and interpret, and galaxy collision blur and the distinction between formation and evolution. So the galaxy formation starts in the very early universe when small density fluctuation in the matter begin to grow, okay, into the pre-galactic globes of gas. Okay, so how about the mergers and the acquisition? Okay, about the galaxy will grow by the repeated merging of the small object and also formation the large cloud fragment into the small pieces like this. Okay, here. And if we zoom in this part, it's actually there are a large amount of fragment, okay, that break into the smaller pieces. Okay, so the distant galaxy, okay, we have these two, distant and the figure. Here is a blob that contains several billion stars that spread throughout the distorted spheroid. Okay, so you can see the figure is like the distortion effect because of the distortion. And okay, what the hierarchical merging? So it's a process that begin, okay, the billions of years ago and continues to the present day, okay, as the galaxy continue to collide and merge. So the theoretical evidence for this merging is provided by the computer simulation of the early universe. And we have the observational evidence also, which comes from the high redshift galaxy, okay, which look distinctly smaller and more irregular than those found nearby. And this one is the Hubble Deep Field North, okay, HDF, and a remarkable image taken by the Hubble Space Telescope that's showing the billions of years of galaxy evolution in a single tiny patch of the sky. Okay, so this contrasts with a backdrop of small, faint, irregular galaxy that lying much further away. Okay, so overall, for the galaxy color, composition, and the appearance will change a predictable way as the cycle of stellar evolution recycles and enrich the galaxy interstellar matter. So the elliptical will tend to become fainter and redder in time, while the spiral of or the irregular will continue to have bluish color as long as gas will remain available to form them. So however, the galaxies are usually not left alone, okay, and the interaction and mergers between the galaxy are common. So we'll have the starburst and nuclear activity as their key indicator. Okay, so this galaxy interaction will observe locally are extension of this same basic process into the present day. So this is the evolution and interaction will happen in the accreting material that contained within the dwarf galaxy help to grow the bigger galaxy. Okay, so now the star formation from the time since the Big Bang formed here. So that will be the peak, the maximum star formation rate about 0.1 and above. And after that it will gradually decrease with the time. Okay, and now we have in this present day. So this hierarchical merging accounts for the numbers and total mass, okay, including the dark matter of galaxy over the history of the universe. However, it has difficulty explaining the both of distribution of gas in galaxy and star formation rates up to the present day. So many these galaxies have a asymmetric or wrapped gas disk, okay, often which more far above or below the disk plane that would be expected from the theory. And the formation rate in the universe is larger than we would expect, okay, that's seemingly enhanced and prolonged by the continual infall of fresh gas from the intergalactic space. So what is the galactic cannibalism? So it's a type of a merger that happens when a low mass galaxy in interacting pairs spiral inwards and get disrupted in the center of supermassive galaxy. This is all due to the interaction of their halos within a galaxy cluster. So for example, the spiderweb galaxy here with small galaxy merging into a single huge object. Okay, so when we zoom in this part, so we can see the small galaxy that merge into a single huge object. Okay, so this one is Sagittarius dwarf galaxy that on its way to be swallowed by the center, and Magellanic Cloud will eventually meet the same end here. Okay, it will be make a circle and circle here, maybe around first round, second round, and until they will eventually meet the end, the same end. And the disruption of a dwarf galaxy by the Milky Way would leave behind a tidal stream, okay, with a similar orbit and composition. Okay, now we have the Sagittarius stream, okay, are observed in the SDSS, and this stream will orbit the Sagittarius dwarf over the past 500 million years. Okay, this is from the computer simulation that shows a smaller galaxy can be stored, and the larger one causing spiral arms to appear and triggering extended episode of star formation. So this simulation mimics the interaction between the Whirlpool Galaxy M51 and its smaller companion, an irregular galaxy that may have drifted away million years ago. So this changes here against the time. So if two galaxies collide, uh, there will be a comparable in terms of their size, mass, and then the merger can destroy a spiral galaxy disk and creating a galaxy-wide star burst. So we'll create this hot intra-cluster gases, and once the star formation has subsided, so it will result the object will look very much like an elliptical galaxy with hot X-ray halo left behind. So the random event, and here is the collision and close encounter will be referred to the random events and evolutionary connection between the galaxy, and major mergers tend to destroy the galactic disk, okay? And also what happened in the minor mergers, okay? And this is the most likely how large the spiral, for example, our Milky Way grow. Okay, so the spiral galaxies are relatively rare in the region of the high galaxy density. So since they are fragile, these are easily destroyed by collision. And we have a common spiral happening in larger redshift. Okay, and also these are also isolated elliptical galaxy in low density regions. Okay, so about the quasar, the fact that the quasars are more common at great distance from us demonstrate that they are much more prevalent in the past than are today. Okay, starting the process at least 13 billion years ago. So the most quasars have redshift 2 between 2 and 3 and representing early stage of the galaxy evolution, and their luminosity can be counted by the black halo energy generation mechanism. Okay, so it will become a relatively weak active galactic nucleus. Okay, so in the recent years, many bright normal galaxies have been found to contain supermassive black holes. For example, NGC 4258 that observed using VLBA reveal a group of molecular clouds swirling in high speed about the galaxy center here. Okay. And the Doppler measurement show a warp spinning disk that center precisely in the heart of the galaxy. Okay, so the black hole masses in the observation come to the conclusion that every bright galaxy, whether active or not, contains a central supermassive black hole. So there is a correlation between the masses here in the y-axis and the central black holes and the masses of the bulge of the galaxy in which they reside. Okay, so they combine all the type of a galaxy before, and we can see the correlation between the mass of the black hole and the mass of the bulge. So the reason for this correlation is not fully understood, but this suggests that the evolution of normal and active galaxy must be very closely connected. Okay, so the process whereby the first black hole formed carry the history of the universe and can be understood until now. However, simple estimates suggest the accretion rates needed to power the quasars are generally consistent with black hole masses inferred by other means, and it's spending only little time in their highly luminous phase. Although the fuel was abundant at early times in the universe history, the black holes themselves have yet to form. Okay, and we got these small black holes formed by the first generation of star. Okay, and it's still forming a parent galaxy and merged to form a single more massive hole. Okay, and eventually it can form the supermassive black hole. So some from these sources, SMBH, from this supermassive black hole may have formed directly by the gravitational collapse of the dense central region of protogalactic fragments. Okay, so this is about the quasar epoch. Okay, so I think we stop here for the quasar epoch, and we will continue in the next lecture. Okay, thank you.